Okay, so we're looking at 6.2 out of the textbook, the first volume section in problem number 8, which says to let B be the solid whose base is the unit circle. So I'm going to start by drawing that here. Let me switch to black real quick. And our unit circle, we're going to draw, I think, just the two-dimensional version of this for now, is going to be, here we go, we had x squared plus y squared is equal to 1. So we've got ourselves a unit circle with a radius of 1, which is what makes it a unit circle here. And it says now that our vertical cross sections are being taken perpendicular to the x-axis. So we know that we're going to be drawing a line segment that runs vertically here, as it said, perpendicular to the x-axis. That tells us right away, guys, that this is going to be a dx problem and not a dy. So we have, we've talked about like a concrete base or a foundation. That's what we poured right here. And now, out of those vertical pieces right there, problem 8 says we're going to be making equilateral triangles now that are going to be sticking up out of the XY plane and coming kind of at us that way. If you wanted to draw the three-dimensional version of this, and there's really no need to do it if you don't like doing it, but the way we've kind of drawn this before is that our x and our y plane would look something like this, and that circle would still be circular, but it would look a little bit more elliptical, and then that vertical red piece that I drew would be right here, and now you would start to see an equilateral triangle coming up out of the xy plane and into the z plane there. Okay, and so that's kind of what this would look like here, guys. We've had an equilateral triangle, so that piece would be congruent to that piece, which would be congruent to that piece, sticking up out of the XY plane, kind of up into the air. So they asked us here to show that the vertical cross sections have an area of, and they give you the formula. We would have had to come up with that anyway, even if they hadn't told us. So we'll verify that in a second. And then they want us to compute the volume of this region right over here. So what we're going to have to do is figure out a formula real quick. And again, guys, this is the kind of thing that's not going to show up on a test for you guys. But if we were to look at an equilateral triangle here, oh boy, my hand's getting in the way. An equilateral triangle that would look something like this with all three sides congruent to each other. We would need a formula here for the area of that triangle, which is going to be 1/2 times your base times your height, where the base obviously is the bottom, and the height would be this vertical piece going right down the middle here like that. Well, if we remember some things about equilateral triangles, all of your angle measures are going to be 60 degrees. So we know that that angle is 60. We've got a 90 right here. That leaves 30 degrees. Oops. Okay. That leaves 30 degrees left over for this angle. So we have ourselves a 30, 60, 90 right triangle. This piece right down here is half of the bottom side. So that piece is going to be b over 2 or a 1/2 b. Let me go with that, a b over 2 for the length of this piece here. And the height then, right over here, is going to be this short leg, b over 2, multiplied by the square root of 3. So I guess we could write that as root 3 over 2 multiplied by base. And that, I don't know what I just switched to right there, that is your height. So back to this formula now, the area of that equilateral triangle is 1/2 times its base, and the height we just said right here is root 3 over 2 times b. So cleaning that up just a little bit, area of an equilateral triangle, I should really put tick marks right there, is going to be a root 3 over 4, and then times b is going to give us b squared. So there's a formula for the area of an equilateral triangle. And again, you guys are not going to have to come up with that on a quiz or a test. I would give you that formula if you needed it. Now, back to this problem right over here. If we take a look at the two-dimensional drawing on the right, this vertical piece right over here is the base of that triangle there. So we need to come up with a way of representing that piece right there, which is b, in terms of our variable of integration, which is going to be x. So the way we're going to measure b is do top curve minus bottom curve, but this gets to be a little bit of a pain here. I should probably have written down that the equation for the unit circle here was x squared plus y squared is equal to 1. And the problem here is that's not solved for y. So to get y by itself, we're going to subtract the x squared and get y squared is equal to 1 minus x squared, and then take the square root of that and get y is equal to, and it's plus or minus the square root of 1 minus x squared. And we need to remember that the positive square root of 1 minus x squared is what gives you the top curve here, and the negative square root is what gives you the bottom curve. So here's where this problem gets a little bit interesting. To find b as a function of x, it's going to be top curve right here minus bottom curve. And the top curve is the positive square root of 1 minus x squared minus the bottom curve, which is the negative square root of 1 minus x squared. Okay, and that minus negative is just going to become a plus. So b of x then is a positive square root of that plus another one. We're going to get a 2 times the square root of 1 minus x squared, and that's what b is going to be. Okay, so now what we're going to kind of do here, guys, is a composition of this idea and this idea together right here. So let me switch colors on you here. Let's go blue for where we are right now. We're going to be finding area here of each triangle as a function of x. So I'm really following this formula right over here. So that starts with a root 3 over 4, but now instead of a b squared, our b value comes from right here. 2 times the square root of 1 minus x squared. So there's b, and don't forget to square that right here. Okay, interesting now. Let's see if I can slide all this up. I thought there was a way to do this. Okay, there we go. Move things around a little bit here. 2 fingers? All right, well, we'll go with something like that for now. Okay, so with the, oh, that's right. If I draw something down here at the bottom, then I can scroll wherever I want right there. Okay, undo that, back to here. Hey, now we're in business. Okay, so let's see if we can clean this up a little bit. We're squaring this binomial right here, so this 2 gets squared and becomes a 4, which is going to cancel with this 4 right here. This square root gets squared, and the square root just disappears. So a of x then is going to equal a root 3, and then just times the quantity of 1 minus x squared, because again, the square root and the square cancel each other out. Now, as I go back and read the problem again, I'm reading directly from it here, show that the vertical cross sections have area. A of x is equal to the square root of 3 times the quantity 1 minus x squared. That is exactly what we came up with right over here. So that's the first thing they were trying to get us to do in this problem here. And now, okay, with that in mind, let's go here. Now that we found a of x, we're ready to go ahead and find our volume formula. So here we go, everybody. Volume is going to equal an integral here. And we're going to go ahead and take this one with respect to x, and our integrand is going to be this a of x formula we just came up with. I'll put the root 3 out in front and then just integrate the 1 minus x squared taken with respect to x. And the only thing we have yet to talk about here, the limits of integration, the lowest and highest values of x in this particular region. So if I scroll down here a little bit and kind of look back over here at the original circle diagram we had, the lowest value of x, oh, I'm all over the place, the lowest value of x out here was going to be -1. The highest was going to be +1. We could do this with respect to, from 0 to 1, and then double it using the symmetry of the region. If you're using your calculator, that's not really necessary. And with this one, yeah, I think I'm going to leave it at that. So I tell you what, I probably would go from 0 to 1 and then just cram, oh boy, then just cram a 2 out there in front of that root 3. So this is a mess, everybody, and all of this, though, is what we would type into our calculator. A 2 root 3 times the definite integral from 0 to 1 of this integrand here, 1 minus x squared, taken with respect to x, which didn't need to be over there that far. And let's see, do I still have a calculator set up on this one? Let's see if I do. It was somewhere. Education. I got to download that. All right, I'm going to trust that that one's going to work out. Nope, not that one. That one's going to work out okay and get us the answer then in the back of the book. If not, you guys let me know.